everybody. It's Monaco. Lecture 3, homework lecture 3 in atomic theory. This is the first Google Classroom assignment you'll have on our Google Classroom. We're going to cover the evolution of the atomic model today. So this is from Democritus to Niels Bohr, how the experiments changed the way we thought of an atom. Okay, so the first thing you got to know is, who the heck is this Democritus guy? Well, he pioneered the idea that there's a smallest unit of matter. He gave that idea the word atomos. And this guy was like 400 BC, and it was just a thought experiment, and he thought to his head, if I cut a grape in half, and then the half in half, and et cetera, et cetera, et cetera, furthermore, just cutting it in half, eventually, won't I get to the smallest unit that I can call grape? And I'll call that an atom of grapes, or apples, or rock, or tree, or whatever it may be. Turns out, he actually had a great idea. It had to have some truth to it, and that's why it has persisted for so many millennia. It took quite a long time for the rest of science to catch up with this idea, and it wasn't until John Dalton in the 1850s realized that elements are made of atoms that are very, very small. Okay? And atoms of a given element are identical. And these are his rules. These are called Dalton's postulates, Dalton's atomic theory. Atoms cannot be broken down, created, or destroyed. So these are all the things that Democritus was thinking about 450 BC. 2,000 years later, somebody can actually prove it. That's the nature of the evolution of science. Atoms of different elements combine in simple ratios to form compounds. So atoms can be used as building blocks to make more complex things. And lastly, in chemical reactions, atoms are combined, separated, or rearranged, but they are not destroyed. They obey the law of conservation of mass. Okay? They can be rearranged in any way you want, or any way that's allowed, but they cannot be created or destroyed. Dalton's model of the atom was called the plum pudding model, I believe, and it was Thomson. Haha, I almost got it. See? Got to get these straight. Thomson came after Dalton. He developed the plum pudding model of the atom. Dalton didn't really model the atom other than a sphere. There's plum pudding. Well, he said that the electrons have a negative charge. He discovered this. And the rest of the atoms got to be like this positive goo that kind of holds the electrons there, kind of like a chocolate chips in a chocolate chip cookie. If you think of the chocolate chips as the electrons, the rest of the cookie is the positive charge holding them together. Well, that came after he discovered that first subatomic particle, which was the electron. And he assigned it a negative charge as a result of the cathode ray experiment. He saw that it was responding to magnetism. And as we know, we've got positive and negative ends of a magnet. And he saw that the positive end of the magnet, in the deflection coils here, pushed the electrons away. So the electrons traveled through. Then they saw the positive end and the negative end there. Maybe I got this backwards. Opposites attract. So I got, the positive ends on the opposite side. So, and the negatives down there. They saw the positive charge of the magnet and started to bend towards it. And that's why he said, okay, electrons are negatively charged because they bend towards the positive side of a magnet and away from the negative side. So he knew opposites attracted and like things repelled. So by convention, they said, the electron is negatively charged. And we've held on to that ever since. Next guy, Ernst Rutherford. Rutherford performed a very famous experiment called the gold foil experiment. And here's a little picture of what it is. The gold foil experiment shot alpha particles, which were positively charged, at a piece of golden foil. Most of them went straight through the gold foil. Some of them bent off at odd angles for some weird reason, and others yet, even still, bounced straight back, which was odd because they knew alpha particles had a positive charge. And again, they knew opposites attract and like things repelled. So Rutherford's experiment led him to believe that there's a positive dense center in the middle of an atom, and he called that the nucleus. I believe that's because they already knew about the nucleus of cells, and in a cell, the nucleus is at the center. So there's a little crossover from chemistry, physics, to biology. Now, the other thing that he rationalized was, because most of those particles went straight through, is that most of that atom is really empty space. It's really mostly nothing, which you can see here in his evolution of the model of the atom. He took Thomson's idea that electrons exist, and he put them outside, and he took what he found is that there's a positively charged dense center and put all the positive charge in the middle. So there's Rutherford's model of the atom. This is the model of the atom you would see in popular culture, where electrons are spinning around the nucleus most likely. But let's move on to Niels Bohr, who really gave us what we know and use as the model of the atom. He refined the model to explain its behavior. Atoms emit light when zapped with energy, colored lights, and he needed to explain that. And the way he did it is by explaining electron states around the nucleus. Okay? And what he said is that when an electron gets hit with energy, see here in energy level 1, it jumps up, in this case, to energy level 3, it looks like. Okay? But that's not all. It comes back down when it's not getting zapped with energy anymore. So what happens is it falls back down from 3 back to 1. So we went from 1 to 3, and when it falls back down, you can see that colored light comes out of a very specific wavelength. Related to that transition, how far the electron traveled determines the amount of energy and light and color of light that comes out. So he showed that the orbitals are truly actually energy levels where electrons are located, and that the possible electron orbits are just areas of probability, okay? In reality, you see over here this little pyramid. This is the true shape of all those electron orbitals. This is the first level, there's the second, there's the third, and there's the fourth. You can see how we needed to simplify that complex triangle into something that was a little more usable in this class. So the first level is a circle, the second level is a circle, the third level is a circle, and the fourth level is also a circle. Let's see what else we've got here. The wave mechanical model is that picture. So Bohr helped create the wave mechanical model, which is our modern model of the atom. It's the most accurate, but it's also the most difficult to understand in the sense of how the electrons behave. Complex mathematics called quantum physics are what determine the shape of these orbitals and the behavior of the electrons in them. So we don't really need to do that. So we simplify that the electrons travel about the nucleus as orbits like planets, but they really actually travel randomly in those orbitals that have these funky distinct shapes. And on top of it all, electrons have spin, so they can spin in one direction or the other direction, et cetera, et cetera, et cetera. We don't get into that. What I need you to know about the wave mechanical model and the model of the atom is that it has evolved over time. From Dalton's billiard ball model, which was just like Democritus's idea, to Thomson's plum pudding model, to the Rutherford model, which we see very similar, to the Bohr model, which explains why we observe electrons to behave certain ways, to the quantum mechanical model, which still has yet to be refined further. At the moment, it's been static since about the 1950s, I think. So we're going on 75 years of the quantum mechanical model without any new modification. So we chemists and physicists think that we've got the model of the atom pretty well figured out. For hydrogen, that is. Because that's what the entire wave mechanical model is based on. Just hydrogen. As soon as you start adding other electrons and protons and neutrons into the mix, the mathematics becomes so complex that you need supercomputers to do it. So I think that is it for this video. So you've got a Google Classroom. assignment to finish here. And that's it. Thanks for watching.